cohomology in general. So what even is it? Well, I want to let G be a finite group, and the spaces that I'm interested in are C.CW complexes. So these are formed by attaching orbit cells, G mod a subgroup across a disk, and you attach them via the usual push-out diagram, but with equivariant maps everywhere. And Redon defined a cohomology theory, an equivariant cohomology theory, so it takes into account the G action on these spaces. And once you start trying to compute this cohomology for C.CW complexes, you notice pretty quickly that you need coefficients not just in an abelian group, but in an entire coefficient system. So what I mean by that is I need to know the values of this cohomology on each of these orbits, so I can evaluate it on the cells. And anytime there's a map between orbits, I need an induced map on cohomology, and so that's roughly the data of a coefficient system. Okay, but now if you have V a real representation of G, well, you have this vector space with the G action, so you can one-point compactify and you get a sphere. And now that you have all of these interesting spheres in this equivariant setting, you can talk about the Vth suspension of a space, which just means smashed with this representation sphere, SV. And you might want an equivariant cohomology theory which plays well with these suspensions, has a nice suspension isomorphism. And there is such a theory, and it's ROG graded. So ROG is the Grothendieck group of real representations of G. And you'll see why we need that in just a moment. So it's a theorem due to Lewis, Peter, May, and McClure that this ordinary integer graded cohomology that Redon defined with coefficients in some coefficient system extends to an ROG graded theory if and only if that coefficient system extends to a Mackey functor. So I haven't really told you what a coefficient system is very precisely, and I also am not going to tell you precisely what a Mackey functor is, but roughly it's a coefficient system with some extra backwards maps so that everything's compatible. So it's kind of just a souped up coefficient system. But what this says is that for alpha in ROG, so some virtual representation, meaning some sum or difference of actual representations, and a Mackey functor, souped up coefficient system, I can talk about the alpha cohomology of some C.CW complex. And this has this nice suspension isomorphism that we wanted. So I can compare the cohomology of X with the cohomology of the Vth suspension, and I see a shift in the indices, just like I would want, only now it's a shift by V. So you can see here I need to be able to add and subtract V's from the indices, and that's why we grade on the Grothendieck group of real representations. Okay, so that was a quick crash course in ROG graded cohomology. But now I want to specialize to the case where G is C2, the cyclic group of order 2. So this is where my thesis work is. And in this setting, we have two orbits. So there's a point, C2 mod C2, and also C2 itself. And there are two irreducible real representations of C2. So I've got the one-dimensional trivial representation and the one-dimensional sign representation. And so any representation is going to decompose as a thing I'll call RPQ. It just means some number of trivial representations and some number of sign representations. But I'm going to set this up so that P is the dimension of the representation, and Q tells me the twisted dimension, or the number of sign representations. And the reason for that is that now when I look at the one-point compactification of one of these, I will denote that SPQ. So this is a sphere, and it has topological dimension P and what I call weight, or twisted dimension Q. Okay, so let's look at some examples because it's good to have these in mind. If I take the trivial one-dimensional real representation and I one-point compactify, I get a trivial action on the circle. But if I take one copy of the sign representation, I should get a circle, but with an interesting action. And that sign representation has this reflection action, so I see that reflection action here on the circle. And notice the point at 0 and the point at infinity are both fixed. Okay, I won't take you through all of these, but maybe let's look at S22. So this is two copies of the sign representation. So in the plane, I'm reflecting in the x-coordinate and the y-coordinate, so that's a rotation in the plane. And when I one-point compactify, now I get a rotating sphere. So that's this rotating sphere, and again, the north and south pole are fixed. Okay, so just some examples to have in mind. For this work, I'm going to fix coefficients in the constant Mackey functor F2 underline. So I haven't really told you what a macufunctor is, and I won't quite tell you what this is, but it's really just the closest equivariant analog to F2 coefficients here, so in the field with two elements. Okay, so instead of writing this H superscript V sub G, this is now a bigraded theory because all my representations decompose. It's trivial and sign representations. So I'll just write HPQ of X, and sometimes I'll probably forget the coefficients, but I still mean coefficients in F2, constant F2. Okay, so we have this cohomology theory, and we might want to compute it for some spaces. And so I'll start with the stupidest space you can think of, just a point with the trivial action. And here it is. So I call this M2, and this is supposed to represent the cohomology of a point. And I won't tell you quite how to get this computation. If you're interested, we can talk later, or I can send you some resources. But let me just tell you what this even says. So when I draw these pictures, I'm drawing that topological dimension P on the horizontal axis, and the vertical axis will be my weight or twisted dimension. And I see here roughly these two cones. So every lattice point inside the cones represents a copy of F2, the abelian group, or field with two elements. And this upper cone is polynomial in these elements rho and tau. Then there's a little bit of a gap here, and in by degree 0 minus 2, I've got this element theta. And theta is infinitely divisible by rho and tau. So what I mean by theta over tau is this is a class that when you multiply by tau, you get theta. And this is infinitely divisible, so these cones go on forever in both directions. And, oh yeah, theta squares to be 0. And in fact, everything in the lower cone squares to be 0. But so because this goes on forever in both directions, this is actually an infinite dimensional non-Noetherian ring. So that's sort of unfortunate. The cohomology of a point is infinite and also a non-Noetherian ring. But there you have it. So sometimes I'll be kind of lazy and just draw the outline. This is kind of a lot of data to keep track of, so I'll just outline the two cones and emphasize the generator. And I still mean that this thing is filled in with all of these F2s. So that's M2, the cohomology of a point. And remember that we built the suspension isomorphism into our ROG graded theory. So I already immediately know the reduced cohomology of any of my representation spheres. I just want to take one of these copies of M2 and shift it so that it's generated in by degree PQ. Okay, so I know the cohomology of a point and the cohomology of any representation sphere. There is another orbit, so let's look at that cohomology. When I talk about these cohomologies, I'm really going to talk about them as M2 modules, because there's always a map from any C2-CW complex to a point. Just crush the whole thing, and that's equivariant. So I can always talk about the cohomology as an M2 module, and that's what I'm trying to depict here. So this is the cohomology of C2, and again, my dots represent F2s, and now they're all concentrated on the Q axis. Remember, this P is topological dimension, and Q is the weight or twisted dimension. These vertical lines are representing multiplication by tau. So I'm showing you this picture as an M2 module. And multiplication by rho acts as 0 here, and theta also acts as 0. So if I wanted a nice algebraic description, I might describe this as F2 adjoined tau, tau inverse. But okay, here's the cohomology of C2. Again, I haven't told you how to do this computation. This one in particular is not hard. But okay, now we know the cohomology of a point, the cohomology of any representation sphere, and the cohomology of the other orbit, C2. There are some spheres which are not representation spheres. So I get a free action on a sphere by taking the antipodal action, and this is the cohomology of that. Of course, it's not a representation sphere because any representation has at least the origin fixed. So, okay, it can't be a free action. But I go ahead and I compute its cohomology, and I get this sort of infinite vertical strip. So this is supposed to go from dimension 0 to n. So I guess I've drawn the cohomology of S3 antipodal here. But again, the vertical lines represent multiplication by tau, and now the diagonal lines represent multiplication by rho. And again, theta acts as 0. So I could describe this as F2 join tau, tau inverse, and rho, mod some power of rho. Okay, that's again a lot of data to keep track of, so I tend to just sort of draw the outline and some dashed lines to represent that same thing. Okay, so these are some cohomologies of spaces as M2 modules. And you go about starting to compute cohomologies. And usually the game I play is to find some cofiber sequence, get a long exact sequence in cohomology, and then sometimes have to solve some extension problem. So when you do that,
Clover, this is Dan. Can you go back one screen? I was just curious. You know, these are modules over the cohomology of a point, right? So is like that theta part like acting trivially here? Or
yeah, I don't actually have a way to draw the picture of how theta acts, because theta acts as 0 in all pictures. And actually we'll see that theta is kind of special for that reason. But yeah, so theta acts as 0 on all of these. And I guess you can see that because, for example, tau times theta is 0, and none of these have any tau torsion. Okay, so when you're doing these computations, you run into all sorts of M2 modules. Remember, we're talking about modules over non-Noetherian rings, so they can be really quite complicated. And here's kind of an example. So maybe I've got a differential that's going from one copy of M2, generated here by degree 1, 0, this red copy, and it maps to theta on this blue copy of M2. So here's the generator, and here's theta times that. And if this kind of differential happens, well, it would be an M2 module map. So this class sort of annihilates theta, but then tau times it should go to tau times theta. And as we just said, tau times theta is 0. So, okay, that class representing tau is going to be in the kernel. Remember, these cones, when I draw them, they're filled in. So there's also something like rho tau here, and that will be in the kernel as well. And because theta squares to 0, you'll see that there's no interesting map down here. So moral of the story, this was the only thing that happens here on the p-axis. And so here is sort of an outline of the kernel and co-kernel. And now I typically have some sort of extension problem where I'm trying to figure out how this module might sew up. Here's maybe another example of a differential. So I have, again, a copy of M2, but now it's a little bit higher, and it's mapping to some power of tau on another generator. And then tau times that will hit tau times it, rho times it will hit rho times it, and so on. So this sort of cone kind of eats out the upper part of this cone and leaves me with this strip in the co-kernel. And when something like this happens, it turns out the lower cone will have some piece of it come and hit this blue lower cone. And so, okay, here's a picture of the kernel and co-kernel. And part of what I mean by an extension problem is maybe there should be some row connections here or something. But okay, so these are some examples of differentials, some M2 modules that you might encounter in the wild. Here's another example. So I'm thinking of this as a submodule of M2. So this is like theta up here, and it's generated by theta over some number of rows and taus, theta over some other number of rows and taus, so on. Okay, so this is something that's an ideal. It would make sense to come up. Here's another thing that could come up from some sort of differential. This almost looks like M2, but it's kind of broken into pieces. And so, okay. What I want you to get from this is that there are lots of M2 modules. We're talking about modules over a non-Noetherian ring, and all sorts of stuff shows up along the way in computations. But somehow, miraculously, when you're computing the cohomology of a space, in the end, it always looks pretty nice. So here are some examples. There are 6 C2 actions on the torus, the genus 1 torus, and here are their cohomologies with F2 coefficients. Again, I haven't told you how to do any of these computations, but let me tell you what we have here roughly. So I see in this first example, this is the cohomology of the torus with the trivial action. So I was counting that in the 6th. And I see a bunch of M2s, and they're all generated along that p-axis. So actually right here, I see the singular cohomology of the torus, and that's no accident. In this next one, I see, again, 4 M2s, but now 2 of them have shifted up. And I said earlier that this ROG graded theory extends Bourdon cohomology. What I mean by that is the p-axis is Bourdon's cohomology. So you can see that the Bourdon cohomology would sort of be missing all of this data of these other M2s. This, by the way, is the cohomology of the torus. If you take your bagel and you cut it in half, like you want to spread cream cheese on it, and then reflect across that. Okay, I won't take you through all of these, but some of these look very similar, and then some of them look pretty different. So down here, this one looks like a copy of the cohomology of S1 antipodal, and another copy of the cohomology of S1 antipodal shifted. And you might complain that these two look the same, and they do, they are the same. But if you compute these cohomologies integrally, you'll see you get different things. So these are 2 different tori, even though their cohomologies look the same here. Okay, so these computations.
Clover,
yeah.
I also wonder whether, when you say they're different integrally, I suspect that you could also see that like the cohomology operations are probably different.
That's probably true. Yeah. Actually, I'm not so sure about that. I would have to think about that a little bit.
Yeah, I know.
But one of them, sort of the action reverses orientation, and the other one preserves it. So that's another way to see it without having to go to the integral coefficients. Okay. But yeah, that's a good question. I'll have to think about it. So these computations were joint work with Eric Hogel, and we were computing these cohomologies, and we'd run into all of these strange M2 modules. And then at the end, we would tell our advisor, Dan Duggar, the answer. And really, it was easy to tell him. We just had to tell him where the M2s were and where the strips were and how big they were. So actually, since then, Dan Duggar's classified all the involutions on surfaces, and Christy Hazel has computed all of their cohomologies in F2 coefficients and integral coefficients. So we actually have a lot of data now, which is really cool. But okay, so there are all these weird M2 modules, but somehow the cohomologies all sew up to be these nice things. So that was the theorem I proved in my thesis, that if X is a finite C2CW complex, meaning finitely many cells, then its cohomology just looks like shifted copies of M2, this cohomology of a point, the cones, and the cohomologies of antipodal spheres, which are these strips. So all of these weird M2 modules we encountered along the way can't be cohomologies of spaces. Okay, I should say this result is really kind of surprising. So as it stands, I've only shown you cohomologies that look like this, but you really do run into these strange things along the way computing differentials. And there are so many modules over this non-Noetherian ring, but somehow they all sew up nicely, and we really just get these cones and strips. Okay, a little bit more precisely. So I'm saying that if X is a finite C2CW complex, then we can decompose its cohomology as a bunch of shifted M2s and shifted cohomologies of antipodal spheres. And those shifts correspond to actual representations in ROC2. So recently, I've been able to prove this corollary, which proves this decomposition at a spectrum level. So if you have a finite C2CW spectrum, then you can smash it with HF2 underlined. So that's the Eilenberg-MacLane spectrum representing this theory. And again, I see this decomposition corresponding to spheres, representation spheres, and I guess suspensions of antipodal spheres. So this might seem really obvious. We're talking about C2 things, and we're just getting representation spheres and the other kinds of spheres, but it really is actually quite surprising. And we'll see that this doesn't always work for other kinds of groups. I should also say, by the way, that here, these shifts now correspond to maybe virtual elements of ROC2 since we're in spectra. But okay, so I want to tell you a little bit about the proof. Remember, I'm trying to show that the only M2 modules that show up in cohomology are these cones and strips. And in M2, there are sort of these distinguished elements, tau, rho, and theta. So this gets back to your question earlier. Theta is actually really special. in that it detects copies of M2. So if I have a non-zero theta multiple, then I actually have an entire free copy of M2 inside the cohomology. And that's actually fairly easy, roughly because theta is infinitely divisible by rho and tau. I couldn't have had any rho or tau torsion, and that one's not so hard. So that's why I never draw theta multiples, because they would only ever show up in copies of M2. Okay, the next piece is a little bit more surprising. So this M2 as a module over itself is injective. That's what it means to say it's self-injective. So that's really kind of weird. Injectives are weird, but M2, this non-Noetherian ring, turns out to be injective. So what that means is that now I can detect all my copies of M2 using theta. I include those in the cohomology of my space and take the quotient, okay, and I get this short exact sequence. And because M2 is injective, that short exact sequence splits. So I've now written the cohomology of X as a bunch of M2s and something else. And so the rest of the proof is aimed at showing that this module Q, the quotient, just looks like a bunch of these strips. Okay, so what goes into that? Well, I should say these first two pieces were just actually facts about M2 modules. There was nothing really special to the cohomology. But now I need some actual topology. So for a finite C2CW complex, if you rho localize the cohomology, then you just get the cohomology of the fixed set, the singular cohomology of the fixed set, tensored with a bunch of copies of M2 rho localized. So that's what this looks like. So I just see a bunch of copies of this corresponding to the singular cohomology of the fixed set. And that kind of makes sense. If you look here, everything has rho torsion. So if I rho localize, everything will die. But the antipodal sphere has empty fixed set. So okay, I expected everything to die. Okay, so there's that piece. And then this last piece is that these three elements in M2 give a Toda bracket decomposition of 1. So the Toda bracket of tau, theta, and rho is 1, and that's with 0 indeterminacy. If you don't know what a Toda bracket is, this is some sort of higher order multiplication. But this is really surprising. You don't often see some sort of decomposition of 1. And this was actually first suggested by Dan Isaacson, that we might have this Toda bracket and that it might help prove some Freeness theorems, which I'll come back to later. But essentially the rest of the proof is to use these two pieces together to show that Q is a module over a graded PID and get this decomposition into these strips. So let me say a little bit more about that. So how could we use this Toda bracket to rule out these weird M2 modules and show that Q just looks like these strips? Well, for example, if we know that we have a class in cohomology that's killed by tau, then it has to be in the image of multiplication by rho. And this is just a juggling formula. So if I write X as X times 1, or X times this Toda bracket, since X times tau is 0, then I can shift that bracket, and now I've written X as rho times something. Okay, so how does that play out in some of our examples? Well, we have this weird submodule thing. Remember, this was kind of like theta, and I was thinking of this as theta over some number of rhos and taus. And I'm just drawing the outline here. But if I call this class X, tau times it is 0, there's nothing there. And it's not in the image of rho, so this can't be the cohomology of the space. Here's another example. We saw this thing that kind of looked like a broken M2, I said. So if I call this class X, then tau times X is 0, but it's not in the image of rho, so that can't be the cohomology of a space. You actually do encounter this module when you're computing cohomologies of spaces, and so what that really tells you is that there are rho connections here, and so that's telling you how to solve the extension problem. But okay, so this together with a bunch of sort of similar results using juggling in this Toda bracket, along with that rho localization, we can use to show that Q is a module over F2 adjoint tau, tau inverse, and rho, which is a graded PID. So we get the fundamental theorem for finitely generated modules over graded PIDs, and we get this decomposition that we wanted. Okay, I should also say finiteness is required. So when I first started talking about this, I thought I might be able to extend to the infinite case. And you might hope for that, especially because this fundamental theorem for finitely generated modules over this graded PID showed up. And essentially, I'm just getting torsion copies of that module corresponding to the cohomology of antipodal spheres. But the infinite antipodal sphere has as its cohomology that graded PID that I'm using. So I might expect to just be able to extend and allow free copies. But unfortunately, that's not going to work. So even if I have finitely many cells in every dimension, here's an example with one cell in every dimension, I won't necessarily fit into this structure theorem. So Dan Duggar came up with this counterexample, call it S infinity infinity. And here, if you take the colimit of multiplication by rho, then you get something else. So, okay, rho corresponds to a map of spaces, or you could just think of this as the inclusion of the fixed set. So this is the trivial zero sphere. And I can include it as that north and south pole of that reflecting circle, and then keep suspending that map. Okay, so you compute its cohomology, and you get this sort of diagonal thing that goes forever downward. And that can't possibly look like copies of M2, the cones, or strips, the vertical strips. So, okay, we won't be able to extend. Okay, so I want to show you how you might use this in computations, give you kind of a flavor of how the computations go. So let's look at this space RP2 twist. This is the usual gluing diagram for RP2, and I'm just going to take it and rotate 180 degrees around this point. So that gives me a C2 action. And I can, when I do that, this boundary circle is actually exactly sent to itself. So that's a fixed circle. So I can include that fixed circle as the boundary of RP2. And when I quotient, I should get a sphere, a two sphere. But because I have that rotation action, I'm getting that rotating sphere. So, okay, that's my S22 that we saw earlier. So here's a co-fiber sequence that RP2 twist fits in. And that gives us a long exact sequence in cohomology. And then we run into an extension problem. We've actually exactly seen this one before. So here was that copy of M2. This is the cohomology of S10, right? It's generated in by degree 10. Then I've got the cohomology of S22. So that's an M2 generated in by degree 22. And by the differential, I mean the differential coming from the connecting homomorphism in the long exact sequence in cohomology. So, okay, you can work out that this differential does happen. It's non-trivial. You can see that a couple ways, but this p-axis is Bourdon cohomology. So that's one way, is to compute Bourdon cohomology. In any case, when that differential happens, remember tau times it was in the kernel, rho times it, and so on. And so I get sort of this funky outline for the kernel and co-kernel. And now I have an extension problem. Somehow, this must sew up to be the cohomology of RP2. But the structure theorem says you can only have cones and strips, and those strips have something in every weight. But here, I see there's a gap in the cohomology. Okay, so there are no strips, no cohomologies of antipodal spheres. It can only be M2s, and now you can just count the ranks, and you see there are two copies of M2. This particular case is actually an example of a phenomenon that was known. So I've been talking about C.CW complexes where we attach orbit cells, but you can also look at rep-G complexes, and those are formed by attaching representation cells, the unit disk in some representation. And the Grassmannian of K-planes in any one of these representations, RPQ, is going to be one of these rep-G complexes. So our RP2 twist that we were looking at, you can think of as lines in R31, if you like, and that shows that it is a rep C2 complex. And it's a theorem of Cronholm's that if X is a finite rep C2 complex, then its cohomology is free as an M2 module. So just a bunch of copies of M2. There's actually a really subtle error in this proof, but I have since been able to fix it with Eric Hogel using this structure theorem. So that's nice. Maybe to sort of flesh out the story, what other kinds of theorems like this are known, well, Ferland proved in his thesis, extending work of his advisor Lewis, that if you have a finite rep CP complex where P is odd, and you only use even dimensional cells, well, then its ROG graded cohomology is free as a module over the cohomology of a point. And notice I'm not writing M2 here because you have to work out what the cohomology is in these settings. And for the experts, this particular one holds in Burnside-Mackey functor coefficients and constant integral coefficients. Okay, so I was hoping when I was first working on this to try to prove some sort of freeness theorem here in constant FP coefficients. So I started thinking about CP spaces where P is an odd prime. And that's kind of the story I want to tell you about now. So I want to fix G as C3 just for concreteness, but really could tell almost exactly the same story for any odd prime. And again, there are two orbits. So there's a point and C3. And as long as I'm actually fixing my prime to be 3, there are two representations. There's the one-dimensional trivial representation, but now our interesting representation is two-dimensional, and it's the rotation of the plane by 120 degrees. So when I write RPQ, I really, again, want to let Q be the twisted dimension and P be the dimension, so that when I talk about a representation sphere, again, P is the topological dimension of my sphere, and Q is telling me about the twisted dimension. So back to our examples, notice it's a little sparser now because we don't have any reflection actions when we're looking at C3 spaces. But I've still got my trivial circle, and I still have my rotating sphere, but now that's rotating 120 degrees instead of 180. Okay, for this, I'll talk about coefficients in the constant Mackey functor F3, again, the analog of F3 coefficients. And again, this is a bi-graded theory, but it's important to remember here, it's a little bit confusing, Q can only be even because Q is telling me about twisted dimension, and I don't have any interesting odd dimensional representations. Okay, so we go compute the cohomology of a point, for example, and this picture looks pretty similar. So again, I've got roughly 2 cones. Well, now all of these dots represent copies of F3, but actually things are a little bit different. So you might notice that it looks kind of sparser. I should have sort of 2 dots here, but that would be in an odd weight, and there's really no odd weight here. So this is kind of the first place I could see something happen. Also, this upper cone is roughly polynomial in X, Y, and Z, but I actually have some graded commutativity coming into play here. So Y is going to end up in an odd dimension. And so actually, this upper cone is polynomial in X and Z, tensor exterior in Y, because Y squares to be 0. Then, as before, this looks like a gap, but remember, there can't be anything in odd weights, so there really is no gap there. And there's this class W, and W is divisible by everything in the upper cone. Okay, so I'll call that M3, and that's the cohomology of a point in constant F3 coefficients. I guess this time I've decided to show you a worse depiction rather than the outline, but here this shows all the X, Y, and Z connections. So notice that X times W is not 1, X times W is 0. And once I've computed this, I know the cohomology of any representation sphere. It's just going to be a shift of this thing, so shift to be generated in bi-degree PQ. Okay, so the cohomology of a point, slightly different, but it looks pretty similar. Again, any space is going to have its cohomology be an M3 module, just crush the space to a point, and that's always equivariant.
Hi, Clover. It's Dan again. Sorry, can you go back one slide?
Sure.
Sorry, I feel like I keep asking the same question here. Sorry about that. But
okay.
What about the cohomology operations in the cohomology point? Do you happen to know what they are?
I actually don't know much about the cohomology operations, and I think that Shanu is probably doing some work around that, but I don't know very much at all.
Okay.
Yeah.
All right. Thanks.
Okay, so we have the cohomology of a point, and we compute the cohomology of C3. Again, it looks very similar, right? This vertical line. Okay, but remember the dots now are copies of F3, and now these vertical lines represent multiplication by X. Oh, I should have said, you might have noticed that second M3 picture looked a little bit more squashed, and I just rescaled because really those odd weights are never gonna have anything, so I just wanna see more of the picture. So this maybe looks like it's in an odd weight, but that's really at height 2. Okay, anyway. I guess I haven't put any scale on my axes anyway, so it's a little hard to tell. In this C3 setting, there are no reflection actions, so I don't have antipodal spheres anymore, but I do still get free actions on spheres. For example, S1, I can rotate 120 degrees, and that's a free action, and here's its cohomology. And it kind of looks like that strip we saw before, only now these are Y connections. In fact, any odd dimensional sphere has a free action that quotients to the lens space. And so, okay, this time I guess I admitted I was computing the cohomology of S3 with this free action, but here's roughly what I get. So again, kind of looks like this vertical strip. I've got all those X connections, and now I'm drawing in the Y and Z connections, but they're all the ones that you would possibly hope for. So really, the only one is that there isn't a Y connection here because Y squared is 0. Okay, so I have these cohomologies, I see these cones and the strips, and it seems like I should be able to do the same thing as before, but actually, that's not going to work here. And the problem is this thing that I call the egg beater. So the egg beater is the cofiber of the map from C3 with a disjoint base point to S0. So I'm just crushing C3 to a point. And when I do that, I get these sort of 3 spines rotating in space. And this looks more like an egg beater for large values of 3. But okay, I've got this sort of one skeleton of my rotating sphere. And you go and compute its cohomology, and you get something a little bit different. So here's one depiction where I've sort of shown all the X, Y, and Z connections. And here I've just kind of drawn the outline. But what I want to point out, what's different about this, is that there's nothing on the p-axis. You might remember it looked like there was this gap in the cohomology of M3, but there wasn't really because there were no odd dimensional, no odd weights. But this is on the p-axis, that's where Q is 0, that's an even weight. So this is an actual gap. Okay, and so we see an actual gap in the cohomology of the egg beater. But there was no actual gap in the cohomology of M3, the cohomology of a point, which is M3. And there was no actual gap in the strips. So this has to be something new. Okay, I should point out for C2, why did this thing not come up and cause problems? Well, the 2-spined egg beater is actually just our representation sphere S11 with that reflection action. So sort of accidentally, that egg beater was a representation sphere and we didn't need a new object. Okay, but I claim that actually these are all the things that you need. So for C3, I should need the cohomology of a point, these strips, and the cohomology of the egg beater. So I'll call this the theorem in quotes. This is really maybe a conjecture with a lot of evidence, and it's work in progress. But I claim that if X is a finite C3 CW complex, then its cohomology in a constant F3 coefficients will decompose as the cones, these M3s, the cohomology of C3, sort of this vertical strip. C3 is not actually a sphere anymore, so okay, I'm separating that out, but then there's also the cohomology of all the free spheres, which just look like the strips, and the cohomology of the egg beater. Okay, so I want to tell you a little bit about why I think that that's true. So remember for the C2 structure theorem, we had all of these pieces. So here was M2, which had tau, rho, and theta. And theta detected copies of M2. This thing was self-injective. We used rho localization to relate to the cohomology of the fixed set. And we had this Toda bracket decomposition of 1. Well, in C3, now our cohomology of a point looks kind of like this. I've got X, Y, and Z, and now W is the thing that's infinitely divisible. And W, again, detects copies of M3, really in essentially the same way. This M3 is actually self-injective. So again, it's injective as a module over itself, or as an M3 module. And Z localization now plays the role that rho localization did, where Z localization relates back to the cohomology of the fixed set. And again, we have a Toda bracket decomposition of 1 with 0 indeterminacy. So, okay, you might wonder, then why are we not done? We could do all of the same things. But remember, there's this egg beater. Okay, so none of the old techniques really said anything about the egg beater. So I think the cohomology of the egg beater is injective, and the main problem is just detecting that cohomology of the egg beater, ripping it off, and now sort of futzing with the fact that the strips are no longer quite a graded PID. But okay, I suspect that will all work out. I want to show you how this might play out in an example. So in C2, we had this RP2 twist, but now I want to consider Y. Again, this is sort of a disk with its boundary identified, but now, well, I'm really thinking of it as a triangle, so these 3 edges are identified, or maybe it's a p-sided triangle if you're thinking about CP. And I rotate this, well, if it's C3, 120 degrees. And when I do that, this edge will be sent to itself. Okay, so the boundary is a fixed circle. I can include that, and when I quotient, I get this rotating sphere. And again, there's a long exact sequence in cohomology, and I run into an extension problem. Okay, so we haven't seen quite this one before, though it looks very familiar. There's this M2 generated in by degree 1, 0. There's an M2 generated in by degree 2, 2. Oh, sorry, I should say M3. We're in C3 spaces, and we're using F3 coefficients. This is the disadvantage of just using the outline, is that it's easy to forget that they really are different. So sorry, this is an M3 generated by degree 1, 0, and an M3 generated in by degree 2, 2. And now this differential is 1 hits the thing that looks like theta, but I call W. And again, it's fairly easy to work out that that differential is non-trivial, and everything else survives. So this is sort of a rough outline of the kernel and co-kernel. We see that gap, and so the structure theorem would tell us that the cohomology looks like 2 copies of the cohomology of the egg beater, 1 shifted. And there's definitely a lot of evidence for this, but without the structure theorem, it's hard to say for sure. So, okay, I think that's all I have. Thank you for listening.
Okay, I'm going to, well, let's open up for questions.
This is Doug Ravenel. When you do this for a larger prime, do you get more elements like Y? Do you get what kind of ring do you get for a larger prime?
So in a sense, I really get the same ring. Dylan tried to convince me of this a long time ago, and I was struggling with it. But if I do a larger prime and I work in constant FP coefficients corresponding to the prime, then because multiplication by P is an FP equivalence, then I really can sort of collapse down to a bigrading, and essentially the pictures really look the same. Let me see if I can go back to one, sorry. So, you know, I would have MP maybe, and I'm just choosing the representative that is that sort of first p-th root of unity here to give me this bigrading picture, but it really is essentially the same once I collapse.
Wouldn't you have let's say the prime is 5, wouldn't the weight be divisible by 4?
No, so I still have, what happens if the prime is 5 is I have a 1-dimensional trivial representation, and now I have 2 2-dimensional rotation representations. So one is rotation by 72 degrees, I think, and one is 144 degrees. And I'm choosing those representatives. And I guess I'm saying P locally, that rotation by 72 degrees is equivalent to rotation by 144 degrees, even though they're not isomorphic representations.
Right. Okay.
Yeah, so actually in integral coefficients, I think then we're in quite a bit more trouble. I don't know what we'll say there.
Other questions?
I have a quick question. That, you know, with the Toda brackets and the row divisibility, is that like an other incarnation of the gold relation?
The gold relation?
Doug's?
I'm not familiar with that. Is that something you can say, or should I just look it up?
Maybe, no, Doug can say it.
It's something you see in cyclic groups of order 2, two cyclic groups that have order bigger than 2, like in C4, you see this relation. You have various A's and U's, the things you're calling rows and taus, but you have more than just one of each, and there's certain relations among them.
Oh, so maybe I don't mean the gold relation. I mean that thing like that. So the theorem about the exotic transfers, Doug, in that C4 paper of yours, where like if multiplication by I don't remember how it goes, but by something is 0, then you get some kind of multiplicative extension, like exotic transfer or something. Something has to be a transfer or restriction.
Yeah, right.
All right, so I can point it to you, Clover, and then
okay.
You can.
Yeah, sounds good. I'm not familiar with it, so I can't say right now. But
I'll just send you an email.
Okay.
Other questions? Well, I have a question, or I don't know, maybe it's a comment. I can't help but feel that the infinite complex case, you shouldn't have just given up on the infinite complex case.
I haven't given up.
There
So
must be, okay.
I suspect that, okay, really, maybe I will look at homology, and so I'll get the dual picture, which just looks like that row localized M2 kind of thing. But I suspect that in infinite complexes, that really we can say that we get M2s and these vertical strips and also diagonal strips, and that they can be as big as possible. But there's definitely something a little bit subtle there, because this infinite strip, it was really infinitely divisible by tau rather than not having tau torsion. And so, I don't know, it's just like a little bit more awkward to work with. But that's my conjecture, and I have some evidence for it, but I guess I'm not sure quite how to prove it. The main issue is that in this result, I can use the Toda brackets, but then the fact that M2 is injective means I can rip off those pieces. And once I do that, well then, okay, my hope is that I'm left with vertical strips and diagonal strips, but neither of those will be injective, so I don't know quite how to rip them off. Neither injective nor projective. So yeah, it's just finding the D direct sum decomposition, I think.
And the other comment I was going to make is, you were talking earlier about how the representation complexes only have the cone pieces and none of those antipodal strip things. And so it's like this, so like those antipodal strips are somehow like the obstruction to a C.CW complex being a rep G complex. I don't know if there's some way to make that statement precise or something, but that's kind of what it feels like.
Yeah, somehow all of these strips show up when you have some sort of free cells or some sort of free thing inside it, but then, yeah, I don't know. I also think that somehow is the obstruction to representing something as a rep C2 complex. On the other hand, there are things that have free cohomology. Well, this is maybe a slightly different issue, but there are things where it's not immediately obvious that there is a rep C2 complex structure for it. Or more likely, in most of our examples, we have been able to find a rep C2 complex structure, but we aren't necessarily able to find what seems to be the right one, where there are no differentials, or all the differentials are trivial. So I think yes, but somehow it's not immediate to me.
Okay, other questions? All right, I'm going to unmute everyone so we can thank Clover one last time. Okay, and that's it for today. Our next meeting is on November 29th in 2 weeks. Tom Bachman will be speaking. Okay, thanks everyone. See you then.